Hey everybody, I'm so excited to be here. Shalom everyone. My name is Gil, everybody calls me Dabah, and let's see how it works. All right. So 2 years ago, I wasn't working, I was pretty bored, and what I love to do is reverse engineering. And I said, okay, there is a favorite component, it's called Win32K, which I'm going to tell you more about. And I said, let's take a look and see what's there. Oh, sorry, my bad. And I said, okay, let's take a look. And somehow I find a crazy design flaw. And the point today is to go over it and show you. Again, it's going to be hardcore, but I'm going to go slowly and teach you everything to understand it. Hopefully, I'm going to do a good job. So this tweet was about April Fool's, telling everybody I found like 15 CVEs, and nobody believed me, but then I dropped like tons of POCs on GitHub. So, you know, we are here in a security conference, and then there is another part in the world that my heart goes out to, the Ukrainian people, so I cannot just ignore it, and I have to be here saying that. Okay, so now about our agenda. Introduction is going to be very basic. It's something everybody knows. It's going to be easy. Make sure you keep with the pace. No pressure there. And then zombies. It's all about zombies. We're going to explain what it is, and then we'll see why it's interesting. Exploitation, obviously the good stuff. And then we see why it was like cool wrap-up. So the first thing about Win32K, it's that everything in the kernel is GUI is being done in the kernel, okay? So graphical user interface in the kernel, right? And then we talk about UI objects like windows, menus, buttons, all this kind of stuff. And they're all in the kernel, okay? So you can imagine what can go wrong, lots of things. And the good thing about putting it in the kernel is that now we don't have a transition from user to kernel. Now we have a transition from user to kernel, so it's better performance than transition from user mode to another process in user mode. So back in NT4, they said, let's take it down. It's going to be faster. Everybody is happy. So the bad thing is now, if you took a component from user mode and you put it down in the kernel, now you need sometimes to call back to user mode for Windows messages, for example. So that's going to create lots of problems. And then the ugly thing is the code quality. So not me. It's leaked source code. You can check it out for yourself. So now, the first thing you need to know about it, everything is about user callbacks, okay? So there is kernel calling back to user mode to some stuff that we can manipulate, and that's going to create tons of mess. And now I want to tell you something. You're going to see XXX. It's not what you think, but it is, the meaning of it is to tell everybody else when they see the code, XXX might go back to the kernel, from kernel to user. Sorry, still excited. So from kernel to user, that's XXX. And there is a critical section. So if you try to do it twice from 2 threads going down to the kernel, only one, the faster one, is going to do it. And then up if it needs. OK. So this is a pseudo example. OK, just some simplified code. OK, shit. I'm looking at the wrong one. Nobody tells me anything. Thank you. Amazing. OK, so all the callbacks to user mode, good thing. and then the XXX. So we said XXX goes back to user mode, OK? Good. Now I'm with you. So this example, what we are doing here is to show you like a syscall from user mode calling kernel, and then we create a window, and then we call XXX. Okay, and then we use P again. So the set window style uses P again. And now, can you imagine where's the bug? So we said XXX can go back to user mode. In user mode, we can do the bad things. Okay? So the point now is how we can abuse it. Okay? So let's see how it looks in a normal flow. So the first thing we do, we start from our user mode application. We call down to the kernel, and then inside the kernel, there is the window created, there is some callback, then the callback goes back to user mode. Okay, so get it. Kernel goes back to user mode, and now we destroy the window. And it goes back to the kernel to really destroy the window, goes back to user mode, goes back to kernel, and now what happens? P is used, but it's already freed because somebody destroyed it. Okay, but this is the basic stuff. So the point is that now there is no P. We have the use after free, and we have a problem. So obviously they thought of it, and they fixed it. But before we get to the fix, or just that, so objects are being locked, okay? There are two types of locks. One is like the scope lock, and we will see how it works. And then there is another one that I'm going to skip now for brevity. But the point is, for all the objects in the kernel, you can just call some syscall to create them, to destroy them. And this is the important thing. All the objects start with 0 ref count. Maybe it's not like that intuitive, but that's the case. But the destroy functions, and this is also very important, will only free the object in the kernel when there are 0 references, which makes sense, right? And then we talked about thread lock and thread unlock. I'm like, a sec. This is, OK, we're good. So the thread lock now is the solution for what happened earlier. And let's see why it's a solution. So now we are in the snippet of the kernel. We lock the pointer. As you see, it's a manual locking. If the developer forgets to do it, then there's a problem. We call back to user mode. If we now destroy the window in user mode, okay, what's going to happen now? Nothing. Why? Because the reference count is still 1. Okay? And now we have this spatial situation that's the zombie. And the reason it's a zombie, it's because it's in between weird states. Because on one end, somebody tried to kill it from user mode because we got back to user mode. On the other end, there are still references. So now we have a weird situation. And let's see why it's so interesting. And now we're going to talk about the zombies. The reason it's called zombies is just because I saw in some of the comments in the leaked source code, they said zombies. So I said, OK, it makes sense. But let's see what's the point with the zombies. OK, so we said if we try to destroy a window or any UI object with more than 0 references, then nothing is going to happen. But in reality, it will destroy it, and soon we are going to understand exactly why the first destruction does something, and then it leaves us with some problem. Okay, so now let's see this snippet. When we get back from XXX some callback, and we destroy it in user mode, then there is a thread unlock. So now what happens is the last reference count goes from 1 to 0, and the object was marked to be destroyed. So we try to destroy it. It's not going to be destroyed because there is a reference count. It's now 1. But in this line of code, it goes from 1 to 0, OK? And the problem is, actually, there is still no problem. So now everything is safe. P is going to be freed after the thread unlock. Nobody uses it, and we are good. But let's see where the story starts to become more complicated, OK? If we destroy object and they still have references, obviously they are called zombies. Otherwise, if they don't have any references, they are free for good. So there is no limbo situation, you know? There is no zombie situation. So zombies still exist because if they weren't existing, you know, in case there are like reference to them, then like the situation with the memory is going to be weird, you know? Because again, it's still somebody is still using it, so it makes sense. And then, okay, this is now complicates everything. And that's why it's so hard, and that's why nobody like ever thought of exploiting it. Because if we destroy the window that is now in a zombie situation, user mode cannot access it. So if we have like handle to window, hwind, and we try to call another syscall, it's going to say like invalid handle and good luck, OK? So the point is like we need to find a way, and soon you will see why, to do something about it. So every object has different functionality to destroy it, and every time we will see, maybe in this one, only one example, how to exploit it. OK, so now as we said, once the zombie reaches the last reference count from 1 to 0, then it really frees the objects and doing the destruction. So let's take a look at DestroyWindow API. Everybody knows the window object in the kernel. And the first time we call to DestroyWindow, what is going to happen is that immediately all the linked objects, like child windows, like the icon, like so many other objects, sub-objects or sub-resources, are getting freed, okay, or getting disconnected. So they try to create a situation where there is no problem going to be happening. So that's the first call, okay? The second time, and this is the crazy part, the second time is when you go, again, from the last reference, it's about smash the ref, okay? So the last reference goes from 1 to 0, and then what it does in the thread unlock, because that's a manual like reference count, it calls again XXX destroy window. So the same function that we can trigger from user mode is now being called on a second time. But the second time is becoming interesting because there might be some side effects. Okay, so now this is the key to the exploit. Until now, the background was like, okay, we call user mode, we destroy something, they forgot to lock it, kaboom, use after free. But now, everything is still like zombie stuff. We cannot re-access it once it's destroyed from user mode, and there is a situation that we need to find a way to bypass to exploit it. So like object-oriented programming, when a destructor is called, right, when the object is dying, it calls the destructors of the rest of its members to say everything is going to get freed together with the parent, okay? So can you start calculating something here? Okay, so the smashable site, this is the recipe. So the point was like, let's give a recipe for exactly finding all the places in the code where we can find this extreme case where we have this situation. And I will give an example, but try to follow these guidelines, okay? Dump pointer in C, it's all the pointers, so the kernel we talk about is like C. And it's assigned, like we saw, P equal XXX, create window, so you get that. And then the last decrement reference functionality, like goes thread unlock from 1 to 0. That's something we want to know because that's where we call the second time destruction with the side effects. And we want to control it, okay? Sometimes we cannot have exactly where we want to free other objects at the right location. And then if we manage to control the last place and load extra members, so the destructor might take with it other members, okay? So you see what we are doing here? We chain objects together. So the destructor, once it's called, taking down with it more objects, and we're going to see how it's happening. So then we are going to have use after free of the first pointer. And now there is a situation here. If the first time we call DestroyWindow is kind of cleaned all of its members, so how are we going to reconnect another window, for example, or another timer, or whatever UI objects out there to be part of it? Okay, so this is why things are getting more complicated. Okay, so let's see like the pseudocode implementation of XXX destroy window. As you can see, first thing it does, or not really first, but the interesting thing, it destroys all the children windows. Okay, so imagine you have a window, you created more windows, saying this is my parent window. If you take down the normal without this exploitation, so the parent window will kill all of its windows together with it. Okay, so that's one example of like the sub-resources being leaked and being destroyed together. So just so you start to understand how it works. And then another example, you can release a capture. It doesn't mean, never mind what a capture is. It's old stuff, but it's another object that you can crawl and do like exploitation. Then you dereference the class. Lots of class bugs also in Win32k. And then this is the interesting part, okay? This is where they check the reference number, because as you see, the object destroy, it checks for 0 references. If there are 0, it can really free the object. If there are more, it's going to do one thing, to say, you know what, remember that somebody said, let's destroy it later. When you go from 1 to 0, please destroy it for good, because that's like the last reference, and that's like a destroy object. Okay? Otherwise, it stays a zombie. It skips the if statement, it stays a zombie, and that's the interesting in-between mode we want to be. Okay, so now let's see a super simplified example, but just to give you an idea of how it is. Okay, so this is like a pseudocode, or just a simplified real example of something I exploited. Okay, so it's tons of code, and then we get to the thread lock. We lock the parent window. Okay, so now whatever number of references that window had, now it has +1. Okay, so pwind, some dumb C pointer, is equal xxx create window, but can you see something interesting about it? There is a link between the child window and the parent window, okay? So now, after you know how xxx destroy window is working, you say, there is something here. Okay, and then we go next to thread unlock of the parent window, because we got it one reference up, now one reference down. And this is where the magic happens. Okay, so by now I know it's been a lot to catch up, so I will try to go over it slowly and say, what we try to do here is the thread unlock that you are seeing on the screen, okay? We want to make sure that at that exact point, the last reference of the window, the parent window, is going from 1 to 0. Okay? And now we know there is a cascading effect of all the destructors of the members of that parent window going down with it. So who is it that is going down with it? That's the child window that we just created. But if you remember, if we go back, the destroy all children, it will destroy anything with it. It doesn't matter if it was destroyed before or after, okay? So now, when we said the first UI object reference count upon creation is 0, right? So when we unlock and destroy the parent window, because xxx create window calls back to user mode, we're going to see it in a second. But the point is at this location, both objects are destroyed. And then they will check for null. But now it's used after free. xxx create window thinks like it doesn't think. Everything there was all right. So it returns a valid pointer because it actually succeeded in creating a window. Thread unlock will take both of them down. The if statement is going to pass. And then xxx send message pwind is like used after free. Very easy to explode. OK, so this is how the stack looks. And it starts from the bottom. You can see the open hierarchy and then thread unlock. That's the thread unlock you are seeing here, OK? And then it will xxx destroy the window. You can see it's going to do assignment unlock. So assignment unlock is binding two objects for a longer period of time with like incrementing the reference count. OK, so the point is now the child is going to be freed as well. OK, as you can see, I cheated a bit because this is the real stack, but I was trying to make it easy with the destroy children. But now there will be another xxx destroy window on the child. OK, so now two windows, both the parent and the child, are getting killed. And that's why we have this crazy situation that a zombie is killing another something that it shouldn't have. So as you can see, we kill them both in this kind of chain effect. I just want to make sure it's clear, because I know it's very hard, and to make sure like I'm in the logic. So normally, any questions from the crowd about it? Because I want to make sure it's like clear. OK. OK, so now we need to reload a zombie. OK, and reloading a zombie is very hard because we said it's not accessible from user mode. So if you look at this code, you tell me, Gil, you are a liar, because I don't see how you can connect both windows and destroy the window, and what's going on? Like, you're not telling me something, OK? And that's really true, because I'm trying to simplify it, and soon you will see why it gets crazy. But this is how the stack looks when we try to kill it. So you know it works, trust me. OK, So if we destroyed a window, and we said the first time we call destroy window, it disconnects all the sub-resources, okay? But then something is missing here. So now we need to stack another operation before we destroy the window, but something will happen after that it's destroyed, okay? So yeah, it's kind of a weird situation, okay? Let's see, like in a very easy way, how it looks. So the point is, again, starting from main, we call, from user mode, some kernel syscall, set window long for this example, and then inside the syscall xxx, what happens next is doing some xxx send message, goes back to userland. And then what we do there, we destroy the window, as we know, goes back to number 4 at the kernel, kills the window, but you remember, the window still has a reference, so it's really destroyed, disconnects everything from it, but then it goes back to number 3, back to number 2, right? It's all in the stack, all the return addresses. And then look what happens next. So the situation of number 5 exactly is the most critical thing about this exploitation, okay? Because now that window was destroyed, it disconnected all its members from itself, but now what we are trying to do, reload the zombie, is to attach again some member to it without accessing it again from user mode. So what we have here is a situation where it's a zombie, but now look at this. It's going to change the style, okay? So let's suppose the style was reset. Now it changes the style to a zombie window, something that shouldn't be happening, okay? Because we said we cannot just free the object, because if we free it, like we're going to crash the system or easily exploit it. Okay, so this is the example of how we stack something, because once we come back from destroy, we want to reach a point where we know in the kernel it continues to do work on that object. Okay, so that's the technique to reload it with extra stuff. So instead of changing the style here, what we can do is, for example, just link another window to it, or just link another menu to it, or do lots of stuff. So we bypass the first destruction that cleans everything, and then we cause it to return, like link more stuff to it. Okay. So now we're going to talk a bit about the exploitation. And the problem is the last reference count, it goes from 1 to 0. And there is one obstacle, like big obstacle, that the destruction at the second time, and this is all by design, I mean, they knew what they are doing, okay, with all the manual reference count. And what they said is the second time, we are not going to call any callbacks, because remember, thread unlock is not a safe place to call user mode. Why? Because it's not XXX. So other developers might get confused, and that's what we are doing here, confusing them. So the problem is, if it doesn't go back to user mode, now we have a race condition situation that we need to exploit. And being in race condition situations is really not fun. And I said, okay, maybe I can try. Okay, and remember that. As long as the user critical section from kernel is held, then another thread cannot just get into the same code in the kernel and just catch the freed block or something like that. So the point is, there is no good way to exploit it. Actually, anti-GDI is not protected with the same critical section. So I found some syscalls that with anti-GDI I could get in at the same time and spin on allocation, try to catch the freed block. That's too tiring. It's statistical. I don't like that. And then there are other mitigations I'm going to skip for now. So the point was asking myself, how do I get back to user mode exactly at the thread unlock? Because if I manage to do that, then it's like a synchronous exploitation. There is no race, and everything is easy. So imagine at the thread unlock, it goes back to user mode. I can do pretty much whatever I want from there, catch the blocks. I have tons of time until I get back to kernel. Everything is deterministic, piece of cake. Okay, so that's what I call the ultimate reloading. And at that time, I was like, okay, I need to find something, and I went over reverse engineering everything about how window is created and how the destruction works. And eventually, I found one place that they forgot to check, and I told you, the second time, like the last reference, when it goes in the thread unlock from 1 to 0, they know not to call back user mode. And what I'm trying to do here is to bypass that. So everything is synchronous. Okay, so I found that whenever I create a window from user mode, I can give some extra window bytes. Doesn't matter what it does for now. But the point is they take some pointer from user mode, and once they see that they need to, again, they allocated something, they want in the destruction to free it, okay? So now that you understand how we can do like this kind of stuff, it should be obvious, kind of, that at the XXX call hook, there is something wrong, okay? Or something like we can exploit. Or before that. So, okay, it goes like this. Create window in kernel goes back with client alloc window, and then we can destroy the window. Okay, destroy the window while it's being created, what the heck, that works. But the problem is that if it goes to the end of create window is going to say, is the window really fully created or is it destroyed? If it sees that it's somehow destroyed, it returns null. If it returns null, like we saw earlier, it's not going to work. So I needed to do something to keep it in extra limbo situation on top of a zombie. Okay? And the question, what was that? So let's see what I tried to do here. Okay? I'm registering a class with some like forcing it to allocate back memory in user mode. Okay? And what we see, create window goes back to the kernel. The kernel goes back to number 3, some hook that I need to do in user space. And there I call destroy window. And now the window partially created, not even fully initialized, already destroyed. And then it goes back to number 4. You can see the XXX call hook. And the hook is something that you can easily sign up for and get the hooks. And then what happens at 5? Okay, now I need to do something crazy at 5 that will not reach to the end of the create window in the kernel. Because if we reach that, like the create window is busted. Any ideas? Okay, so let me reiterate why I'm doing what I'm doing. Because once we managed to do this crazy like side effect reloading, when the last reference goes from 1 to 0, at the thread unlock, it will see, oh, I need to free something in user mode, so let's call back to user mode. But this time, they forgot to make sure it shouldn't go because it's the last reference. We said last reference, thread unlock, it shouldn't go. This is the only code that they forgot to check that flag, like internal flag, and that's the exploit. So now I need to make sure that nobody is messing up with the window once I get back to the kernel. Okay? So let's see how I did it. And that's a spoiler. So at number 5, we managed to tell the window to reload it with a user mode pointer. So when it goes back to kill the object, the last reference, it will call back the memory free in user mode. But now what I did was I needed a way to cut the window creation inside the kernel. And the only way to do it without somebody coming in between the rest of the window creation and resetting my pointer, because then it's not going to work at the last reference, is by calling exit thread. So I actually kill the thread in the middle of the initialization. The user mode pointer is keep pointing to my user mode memory. And then at the last reference, what happens is that it's going to call me to free it. Okay, so this was like the craziest part of the whole thing, even though it's like a whole design flaw. I was like super excited that it was so easy to exploit it now. And now it also unlocked new opportunities, okay, like we used to see before. So imagine now there is some unlock notify window, whatever it means. It goes over, it iterates over some array, and now we see that it calls itself recursively. But the point is, you can see that unlock, the last line, we know that there the unlock might be, if we carefully craft it, that it goes from 1 to 0, and then we can call back to user mode. But this time, we don't need to chain more objects. This time, we just need to reallocate the array items, like the sub-menus of a menu, and then it's going to be used after free, because the pointer, as you see, is just keeps on jumping to the next one. So that's like a new way to do something. OK, so to wrap up. So we see that when we call some destructors, and there are plenty of objects, okay? It might be destroy window, menu or window or free timer or lots of other stuff there. But the point is that there is one primary object that I try to destroy. But whenever that primary object is freed in certain locations, I try to take down with it extra objects, like you saw, okay? And the only way to do it, it is with the zombie chain, or reloading a zombie like we saw in the previous code snippet, okay? So that together gives me like ultimate power to go to lots of places inside the code where there is a smashable site, like the last decref can actually free another object that wasn't even locked yet, okay? So that's the idea of that. And Microsoft themselves decided to call it primary versus secondary. And remember that it doesn't leave the crit, and the only way to do it is with the crazy trick with the user mode allocation pointer. So the crazy stuff about this design flaw is that it is a design flaw, so I'm very lucky to be finding it. I'm kind of grateful. But the other thing is that the same problem happened in another mechanism in the kernel. In the same Windows UI component, but another kind of component missed the same kind of bug. So that's kind of crazy. OK, so then I reverse engineered, actually kind of worked together with them. But the point was that they came up with a crazy, kind of not fun to implement mitigation for this exploit, okay? Because they said, okay, let's start to use C++. It's going to be easier to scope some stuff. But the point was that we know that we chain the destruction of a second object, okay? So they said, if we find this weird situation where there is a second object being destroyed from another primary object, we shouldn't free it right at the same point, because now it's going to be used after free. So what they said is they added a lot of code that, again, in a very sensitive place, that they said, let's queue it for a later destruction. And when is a good timing to destroy objects and being sure it's not going to like screw up things? Once it goes back to user mode, okay? So the crazy thing, it was for me like achievement unlocked, a big one, because for the first time, the guy responsible for the Windows UI kernel got over with me on Teams. And then he just shared his screen and started to show me the patch for the code. And I was doing a code review. And actually, I found a bug there, something that they weren't sure. No, it's really like complicated stuff. I'm really trying to narrow it down, but in practice, it's really crazy. And this is something he sent me in a personal email, like talking with another friend. He said, yeah, like we had 9 people in the team working together on the same kind of design flow bug. So you can imagine it was like pretty big. And I think, you know, as one reverse engineers to you, I think the most interesting thing about the research is not, OK, we exploited it, OK, it's cool. Yeah, we all do that. But the biggest question is like how I started the journey of coming up with this madness, OK? And one day, I sat down, I said, OK, I want to find only one bug to see I'm still, you know, in shape and finding bugs. And then I found this. But you can see the last line, the thread unlock. I looked at the code, and I saw there is some pointer here being used. And I saw something is weird, like this pdesk info, you can see the pointer being used in the while. Nobody is locking it. And I said, like, OK, if nobody is locking it, and then we have somebody calling me back to user mode, maybe I can do something about it, OK? So this was the first line. It took me 2 days. I'm like staring at the screen, like I know it's wrong. I know it's wrong. I don't know how to do it. And then after 2 days, I'm like, okay, I have an idea. And now you know what the idea was and how crazy it was. So that was the first exploit of proving that from thread unlock, I managed to free the pdesk info, and that was a use after free the next iteration. And the crazy stuff was that at this time, I looked at the code and I said, okay, just one exploit, like crazy exploit, but just one of it. And it didn't sink on me at that time that there is a whole design flow yet. So that was over time I started to realize, to generalize what happened here, and to say, yeah, maybe I can make it a pattern, and then I came with the smashable recipe, and suddenly I found like thousands of it. So these are the number of POCs that I actually send them for everything. Now, each one of these POCs, in reality, I didn't even start to tell you how hard it was to change the object and to make sure that the last reference is the one that I can change stuff with it and take down everything. And that was really so hard. And each of them took like a week to work on. So in total, I worked on the thing for like 6 months. And that's what I came up with. So I got like 11 CVs or something like that. And then if it's not enough, this was like more places, more instances of the same recipe that I manually found, because I was lazy to use like CodeQL or something like that. After all, I do it for fun, so it's cool. But then all these places were like, okay, I can exploit it, I'm too tired, it looks good, it looks like I can manipulate all the chaining together, it's going to be fine. And maybe the biggest thing is the number, or the size of the bounty that I got. So I really want to thank Tomer Schwartz and Sar Amar for being the other side, the friendly side of MSRC Israel, to help me achieving this. And yeah, thank you very much, everybody.